If you're trying to, get straight to the core of software architecture, you're in the right place. Today, we're doing a deep dive into algorithm design, which is really that crucial planning phase, right? The step before you write any actual working code.
Absolutely. It's often the difference between code that just worked beautifully and code that, well, collapses under its own weight. Algorithm design is that strategic process. It's about creating a really precise, step-by-step plan to solve a problem with a computer. And the sources we looked at really emphasize its importance, not just for making sure the program works, but for minimizing risk, breaking down complexity.
Making things manageable.
Exactly, and drastically improving the efficiency of whatever you end up building.
And what the source material points out are these two kind of complementary tools, these ways of outlining your thinking. They're basically the plans everyone agrees on before development kicks off.
Yeah, the key players.
We're talking pseudocode, that's the textual way, the language of logic.
Right.
And then flowcharts, which are the visual maps, the diagrams.
And together, they really form this essential contract language, you could say. They make sure everyone, from the project manager thinking about business needs to the developer writing C++ or agrees on how the problem gets solved.
So that's our mission today. Unpack these two really vital planning tools so you can get a handle on outlining logic, whether you lean towards structured text or maybe a more visual blueprint. Let's start with pseudocode, that sort of specific language of logic.
Right. Pseudocode is, it's really the ultimate act of abstraction in a way. Think of it like a formalized rough draft. It lets a programmer map out the logic without getting bogged down by the strict syntax rules of, say, Python or Java.
So it's readable by humans primarily.
Exactly. It's human readable, but, and this is crucial, it uses structured keywords that signal clear intent.
Okay, and one thing the notes mentioned was consistency. Like,
Yeah.
even though there isn't one single official standard, you can kind of make it your own. Mostly using those standardized keywords is really important.
Paramount, yeah. Because they instantly tell any programmer what the logic is trying to do, no matter what coding language they usually work in. You need these signposts,
So what are some core ones?
Well, you define the scope with begin and end. That's fundamental. Then you handle data going in or out with keywords like input, output, read, or write.
Interaction points.
Right. And for just basic actions, clear verbs like get, process, or do, simple sequence stuff.
But the real power comes with the control structures, doesn't it? Decisions and loops.
That's where complexity creeps in and where you absolutely need clarity.
Yeah.
For decisions, you've got structures like if, then, else if.
Or sometimes elife, depending on preference.
Elife,
Yeah.
yeah. Or even when or case for more complex branching sometimes.
And for doing things over and over. Repetition.
For repetition, yeah, that's where you handle tasks that need to repeat. You use keywords like for.
Right, when you know how many times.
Exactly. Or while, if it depends on a condition staying true. Or repeat until.
Which runs at least once first.
Precisely. It executes the task, then checks the condition. These keywords are critical because they dictate the control flow. They tell the system where to go next.
So to actually write good pseudocode, you need a process. The source is laid out 4 steps, right?
Yeah, a clear approach. It connects the idea to the structured form. First step is purely thinking. What's the actual logic? What steps are needed?
Just in your head or on paper, maybe.
Or on paper, yeah. Second, write that down or think it through in just plain English. Simple, clear. This stops you from jumping to code too soon and ensures you're actually meeting the requirement.
Okay, then step 3 is the translation part.
That's it. You convert those plain English notes into the actual pseudocode structure, translating human thought into computational steps.
Yeah, and the 4th step.
Commitment. You must use those key structured keywords we talked about. That's what makes it formal algorithm design, not just notes. Without keywords, it's just description. With them, it's a blueprint for code.
Okay, let's make this concrete. The simplest example is sequence, like calculating a rectangle's area.
Right, super straightforward.
You just go begin, then input length, input width,
If the data in,
then calculate area, length, width,
the process step.
display area. And finally, ND. It's just A, then B, then C, linear.
Yep, simple sequence. But it gets more interesting with decisions, like finding the largest of 3 numbers, num1, num2, num3.
Right, because now the path isn't straight. It has to branch.
Exactly. You can't just compare them all at once, not logically. You need a system.
Step-by-step comparison.
Precisely. So you start, get the 3 inputs, then the logic kicks in. If num1, num2, and num1, num3, then print largest is num1.
Okay, but what if that's not true?
Good question. That's where the structure is key. We use else for the next possibility. So if the first if fails, you check. Else if num2, num1, and num2, num3, then print largest is.
Num2.
And if both of those are false?
Well, then by elimination, num3 must be the largest, right?
So you just use a final else.
Exactly. Else print the largest is num3. It catches the remaining case.
And the sources mention something crucial here, ending the structure. Yes. You must clearly terminate the whole decision block with end if. If you don't, the logic is kind of left hanging, ambiguous, especially if you start nesting if statements inside each other.
Right. Gets messy quickly.
At all FLFC, if LFC ND structure guarantees one and only one outcome. Robust logic.
Okay, I think we need an example that mixes decisions and repetition. That seems like where things can really go wrong in coding. What about that username generation task? Checking the age and putting names together.
Oh yeah, that's a great one for combined logic. Let's say the student's age has to be between 5 and 18. You can't just ask for the age once, right? What if they type something wrong?
You might have to ask again. So a loop.
Exactly. A loop is needed.
So you'd start simple. NPP first name, EMP surname, sequence. But then for age, it's a decision inside a loop.
Right. We could use a repeat until loop, maybe, because we need to ask for the age at least once.
Makes sense.
So you'd have repeat. Then inside the loop block, NP age, and then the decision inside the loop, if age 5 or age 18, then print invalid age entered.
So if it's invalid, it just loops back.
It just goes back to the repeat and asks again. You keep doing that until the condition age 5 ending D, age 18 is finally true.
Ah, okay. That single structure, the loop around the check, ensures you get valid data.
Yeah.
That's a key point of algorithm design, isn't it? Data integrity.
Absolutely. And only after that loop finishes successfully, meaning the age is valid,
Then you do the final step.
only then do you proceed to the process step. Concatenate or join the first name, surname, and the now validated age to create the username. See how sequence, repetition, and decisions all lock together. That makes a complete, robust plan.
That's the textual blueprint then. Very specific, structured, seems essential for complex stuff. But, for really big systems, doesn't pseudocode start looking almost as dense as the code itself? Can it get hard to see the big picture?
That can definitely be a limitation of pure text, and that's exactly why we have the other tool. If pseudocode gives us the structured language, flowcharts give us that immediate visual grasp.
The map.
The map, exactly. That's our pivot.
So flowcharts, the visual diagrams, the pictures of the logic, they use standard shapes, arrows, to show the steps, and crucially, the flow of control.
Right, and this is huge for communicating logic to maybe less technical people or even just for programmers who think visually.
Like pseudocode's keywords. Flowcharts have their own standard symbols, right? You need to know the language of the shapes.
Absolutely. There are 5 essentials you really need to know.
Okay, first up, the oval. That one's easy, right? Start and end.
Start and end defines the boundaries of the whole process. Can't miss it. Second, the rectangle. That's your basic action block.
Any process, task, calculation.
Yep. Any step where something happens, where work gets done.
Okay. Third, the crucial one, the diamond.
The decision point. This is where the path splits. A question is asked, usually yes, no.
And the flow branches out depending on the answer.
Exactly. Manages that nonlinear logic. Fourth, the parallelogram.
Input, output, right? Getting data in or showing results out.
Perfect. Any interaction with the outside world.
Right.
And finally, can't forget the arrows.
They just connect everything and show the direction.
They literally show the direction of flow. They connect the shapes and tell you, go here next.
Okay, let's visualize this. The sources had that simple example, picking the best subject.
Yeah.
You start with an oval, start. Then a parallelogram to input answer.
Get the input.
Then you hit the diamond decision. Does answer equal computer science?
Okay, branching point.
If the answer is no, an arrow takes you down one path, maybe to an output parallelogram saying error, and then to the end oval.
Right, path 1.
But if the answer is yes, a different arrow takes you to another output, maybe correct,
Yeah.
and into the end oval.
Path 2. See how the diagram makes that conditional logic instantly clear?
Yeah, visually obvious. But I imagine this is even more useful for complex stuff like that username loop we talked about.
Oh, absolutely. Think about that repeat until loop for age validation. In pseudocode, it's indentation and keywords on a flowchart.
How does that look?
You'd see an arrow leaving the diamond, where you check if the age is valid, and pointing back up the chart, maybe to just before the input age parallelogram.
A literal loop you can see.
A visual loop. For someone trying to understand the flow, maybe a manager or a junior dev, Seeing that arrow cycle back gives instant understanding. And for really advanced stuff like recursion functions, calling themselves visualizing that loop in a flowchart is often way easier than tracing nested text.
Helps you track the execution path.
And maybe even think about memory use more clearly.
Okay, so we've got pseudocode for specific structure, flowcharts for visual clarity. If we tie these together, what's the big takeaway for someone listening? Why bother using potentially both?
The main benefit really is about reducing risk and getting everyone on the same page. Flowcharts and pseudocode act as that contract language we mentioned. They force agreement on the process before heavy coding starts.
Catching errors early.
Exactly. If you spot a logic flaw, a bottleneck, maybe a missing check on a diagram or in the pseudocode, you save potentially huge amounts of development time and costs later.
So it cuts down errors, not just typos in code, but flaws in the actual thinking.
Right. If you can see the path data should take on a flowchart, it's often much quicker to spot where it goes wrong, like an infinite loop or an unexpected turn, than stepping through lines of code.
Debugging the logic visually.
Which is usually faster. Plus, they serve as great documentation. Months later, if someone new joins the team, they can look at the algorithm design docs, the flowchart, the pseudocode, and understand the core logic without having to reverse engineer the actual code base.
Clear and lasting documentation.
Precisely.
Planning really is key then. We've covered outlining logic with pseudocode's keywords and flowcharts' visual flow. These tools bridge the gap between just an idea and actual efficient software.
Definitely. And if you need one last thought on why this planning is so vital, think about that task in the sources. Design a flowchart for making tea.
Huh. Yeah, seems simple.
Seems simple, right? But even making tea needs a start. Clear steps like boiling water. Decisions like want milk. Now think about the apps you use, daily logging in, sorting email. Imagine the layers of hidden algorithms, the decisions, the steps.
Much more complex than tea.
Way more complex. And if you miss a step in the tea algorithm, like boiling the water, the whole thing fails. In programming, that kind of planning oversight doesn't just mean bad tea. It means huge costs, delays, failed projects.
Good point.
So take a moment, maybe later today. Think about a simple routine you have, brushing your teeth, making breakfast. Could you map its flow using just an oval, a rectangle, and a diamond? What are the steps? What are the decisions?
That basic thinking.
That's where algorithm design starts, that critical thinking.
So use these tools, pseudocode flowcharts, next time you face any complex problem, whether it's code or something else entirely. It really does pay to plan